So the state of matter depends on the strength of the intermolecular forces relative to the kinetic energy from the temperature. The strength of those intermolecular forces depends on the structure of the particles. If we have strong forces, we're going to have substances that have high melting and boiling points. If we have weak forces, we're going to have things with low melting and low boiling points. The intermolecular forces arise from interaction between charges. Those charges can be full charges like ions. They can be partial charges, as in polar molecules with dipole moments, or they can be temporary charges on particles that come and go. But it's attraction between electrical charges. So Coulombs Law is helpful here. This part is just a constant, right? And so we don't actually need to remember that part of Coulombs Law. All we need is that the potential energy is proportional to the charges divided by the distance between them. If we have opposite charges, our potential energy is negative. That's like altitude below sea level. You're just going down and down is more stable. That's where a boulder would roll down through the surface of the ocean and just keep rolling down to the bottom, right? Going to the lowest point possible. So a large negative energy means that there's a lot of attraction. So we have the charges here, and so the magnitude of the charges is going to affect the attraction and the distance between them. The bigger the distance, the smaller the attraction. The smaller the distance, the bigger the attraction. It's like magnets on your refrigerator, right? The magnet, without anything under it, sticks to the refrigerator very nicely. You put one piece of paper, it still sticks pretty good. You stick 10 pieces of paper and try to hold it up with the magnet, it's not going to work anymore. That little bit of distance from 10 sheets of paper is enough of a separation that it won't stick anymore, okay? So force of attraction greater when objects are closer to each other and when the magnitude of the charges is greater. Any questions about that? So we spent a couple of chapters talking about bonding forces, right? You probably learned a little more than you wanted to about that. In a bonding force, we have large charges at very close distances. Protons have a positive 1 charge. Electrons have a full negative 1 charge. And when we get two atoms together and we share electrons, think of whatever bonding model you want, things are very close together. An example is in a water molecule, the distance between a hydrogen and oxygen atom is about 96 picometers. So pretty close. If we're looking at intermolecular forces, the forces between molecules, between water molecules, now the distance is about 300 picometers. So that's 3 times the distance. That's going to significantly impact the amount of attraction. So intermolecular forces are much weaker. We've got smaller charges and we have larger distances. We're going to talk about 4 different forces. The first one is the dispersion force. It goes by a bunch of other names. London forces, London dispersion forces, van der Waals forces, induced dipole forces, all referring to the same thing. I'll do my best to call it the dispersion force because that's what your book uses. So dispersion forces are present in all molecules and atoms. Everything has dispersion forces. Dispersion forces are the result of fluctuations in electron distribution within a molecule or an atom. So here we have an illustration of a helium atom. We've got 2 protons and 2 neutrons in the nucleus, and we have 2 electrons. And this is the 1s orbital, and those 2 electrons are a standing wave in that shape. We could take a picture of them because they are particles and they are waves. We take a picture of them, we force them to act like a particle, and we can see, oh, the electron's here and the other one's here. Take another picture A few seconds later, and the electron are here and here. Most of the time, those two electrons will be fairly spread out, but occasionally you could have both of the electrons on the same side of the atom. This is all of the negative charge in the atom. All the positive charge is in the nucleus. So if all the electrons are on this side, now we have an unequal electron distribution in the atom. One side of the atom, the part where the electrons are not right now, is going to be partially positive, and the side where the electrons are is going to be partially negative. This is an instantaneous dipole. It's temporary, and it's spontaneous. It just happens, and then it goes away, and it happens, and it goes away. This always reminds me of a time when I came, this was a few years ago, but I came into the living room, and all 6 of my children were crowded on half of the couch. They were looking at something on a screen, like, laughing. But they were just like all jammed on top of each other. I'm like, wow, I think I actually took a picture because it was so strange. And then, a few seconds later, they're gone again, right? Because normally they're just sort of scattered about, right? Just like the electrons are. But occasionally, they'll all end up clumped up together, right? So that's what's happening here. Any questions about that? So when this just randomly, spontaneously happens, we get a lopsided atom, right? So here we have the lopsided atom, and now we've distorted the electron cloud to sort of indicate how it's more electron density over here and less over there, partial negative, partial positive charge. This atom having an instantaneous dipole can have an effect on a neighboring atom, because this positive end of this atom attracts the electrons in the neighboring atom. And they're like, oh, we like that, right? They come over here, and that causes this atom to have an instantaneous dipole, which can induce an instantaneous dipole in the next atom, right? And so you can have this kind of chain reaction of induced dipoles. And there's an attraction between them. There's an attraction between the positive and negative charge. So this one gets lopsided and causes this one to get lopsided, and they're attracted, and then this one quits being lopsided, and then that one's like, oh, well, I'm not attracted to you anymore, and it quits too. And so these attractions come and go and come and go. They are very, very brief. They are very small, but they're very frequent, right? A little thing repeated many times can be very significant. Like a drop of water, right? Drop of water, no big deal. Yeah, that drop of water keeps coming, every second a drop of water, and before you know it, the sink is flooded and it's going onto the floor, right? So this is an instantaneous dipole. This is what the dispersion force is. It's the attraction between neighboring temporary dipoles. Any questions? The induced dipole on this one makes me think of taking a cruise on the San Francisco Bay and going out around Alcatraz, right? And so you go out around Alcatraz, and all the people on the boat go to the side that's near Alcatraz because they want to see it, right? You can't see it from the other side. And so all the people go over here, and then that boat kind of starts to tip a little bit. And then this other boat, the people are like, ooh, look, that boat's tipping, right? And so then you could imagine that kind of a weird scenario, just everybody doing that, right? And then the people are going to stop because, oh, wait, we don't want to tip the boat over. So they'll spread out again. So how significant this is, the magnitude of the dispersion force, depends on how easy it is to shove those electrons around, to polarize the electron cloud. To polarize means to form poles, right? To get an unequal distribution, a positive and a negative end. Larger electron clouds are easier to polarize because the electrons are farther from the nucleus. They're not held as tightly. In xenon, need the pointer. In xenon is a much larger atom than helium is. We learned that with periodic trends. As we go down, the atoms get larger. So the electrons, especially the valence electrons on xenon, are much farther from the nucleus. We also looked at how that relates to ionization energy. It's easier to pull an electron off because it's further away. And so I think of a xenon atom as being kind of a big, floppy, flabby, I don't know, like a Michelin Man or something, or the Stay Puft Marshmallow guy, right? Boom, 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 right? And so you can just kind of push them around. And then there's helium. Helium's got 2 electrons, and they're really close to the nucleus. And they can get polarized, but it's harder to push them around because they're held so tightly. So as we go to larger molecules, it's easier to get an uneven distribution, to get the instantaneous dipole. That instantaneous dipole also can be larger, and so the strength of the dispersion force increases as the size of the atom increases. We can see this reflected in the boiling point of these noble gases. Helium boils at 4.2 Kelvin, which is like crazy cold. That's almost absolute zero. And xenon boils at 165 Kelvin. Still very, very cold, but significantly higher than helium. The boiling point reflects the strength of the intermolecular forces. The thing about intermolecular forces is I have all these different analogies that I kind of mash together in my head. So I'm sorry if I get confusing with them. Intermolecular forces are also like Velcro. Okay? So we could imagine these atoms as being people wearing Velcro suits, right? And so if you are in a crowd with other people wearing Velcro suits, it's going to be hard to push between them, right? Because you're going to kind of stick to each other. And so helium has a Velcro suit, but the Velcro isn't very strong. You could think of it as maybe he's just got some little dots of Velcro just here and there, whereas xenon, Velcro everywhere, right? And so this is much stronger Velcro. In order for the liquid to boil, what has to happen is the particles have to completely separate from each other. I have to pull myself away from all the other Velcro people, right? And so if there's a bunch of people completely covered in Velcro, I'm going to have to pull really hard. You might kind of almost need to get a running start to pull away from them, right? Whereas if we've just got a few dots of Velcro on it, it's just a kind of a minor annoyance, and I can mostly just walk away from you. Because we've all had a Velcro shoe at some point where that little flap, it just will not stay anymore, right? It's a piece of Velcro, the Velcro's there, but it's just not going to stay anymore. But I've never actually done it. I probably should. But I've seen these bounce house things with the Velcro wall, and you put this suit on, and you bounce, and you stick on the wall. Right? So cool. So the flap on my shoe won't stay shut, but someone can stick to the wall. What's the difference in the Velcro? There's more Velcro, right? There's a lot more Velcro to get the guy to stick on the wall. It's covering his whole body. If he just had a little square like is on the flap of your shoe, he wouldn't stick at all, right? So small molecules, weak intermolecular forces, not much Velcro. Larger molecules, stronger intermolecular forces, lots of Velcro. So to rip this guy away from the others takes more kinetic energy. Kinetic energy, thermal energy, temperature. So we have to get to a higher temperature before these guys can pull away from each other. The helium takes almost no kinetic energy at all, and it'll pull away from each other. Does that make sense? So the shape of the molecule plays a part in this as well. When we're comparing different molecules, we have to be aware of shape and of molecular size. So what we were looking at with the atoms, we're just looking at size. Here we're going to look at shapes of molecules, and so we want to compare two molecules that are the same mass. So these two molecules, N-pentane and neopentane, have exactly the same molar masses, but their boiling points are significantly different. 9.5 degrees Celsius versus 36, right? Well, what's the difference here? N-pentane has the carbons in a long chain, and so this molecule has more of it's like a capsule shape, right? And neopentane has a central carbon with the rest attached to it, so the molecule has more of a spherical shape. So if you think about these two molecules covered in Velcro, they can stick along this long surface, the side here, right? These two spheres can only touch at a small point, right? So the Velcro cannot hold them together very strongly. It's going to be easier for them to break away. Whereas these guys, if they come up next to each other, they're going to stick along this larger area. Does that make sense? So the shape of the molecule also has an effect on the strength of the intermolecular forces and then the boiling point and melting point. So here's a graph comparing boiling point with molar mass. And here we're comparing molecules that have similar shapes. So we're not comparing round and long, we're comparing long ones. So all of these are straight chain alkanes. What's different is more and more carbons, and so larger molar mass. And we see that it's actually a very nice linear trend here, that as you increase the molar mass by adding more carbons and hydrogens, the boiling point goes up. This molecule, because it's larger, its electron cloud is more polarizable, and because it's longer, this has a lot more surface area where it can stick to each other compared to this one. And so both of those factors combine to make the boiling point higher. Does that make sense? So on an exam, there can be questions like this. There's a lot of put these in order of, or which one has the highest, which one has the lowest. So which of these halogens has the highest boiling point? I2, right? Why? It's the biggest, right? So we learned that the strength of the intermolecular forces is related to the mass, the size of the molecule. And so chlorine is 2 times 35, bromine is 2 times 79, and iodine is 2 times 127. So a much larger molecule. So because the electrons are floppier and can get pushed around more, then it's going to have more stronger instantaneous dipoles and more frequent, and they're going to stick together better. That make sense? Second force is the dipole-dipole force. This is present in all molecules that are polar. So dispersion forces, everything has them. Everything has electrons. Electrons can get lopsided. Everything has dispersion forces. Dipole-dipole force only exists in polar molecules. So you can't have dipole-dipole forces between atoms, because an atom by itself cannot be polar. These forces are stronger than dispersion force. They're the same kind of attraction. The difference is that polar molecules have permanent dipoles. These aren't dipoles that come and go. These are dipoles that are always there. And so the force of attraction is always there, and it's more significant. So here we have 2 molecules of the same compound, and this is an oxygen, and this is a polar molecule, and so we have a partial negative charge here, partial positive charge on the other side, a polar molecule. We could draw our little arrow to indicate the dipole moment. And over here, the dipole moment would be going like that. And so there's an attraction between the negative end of this one and the positive end of that one. It's a lot like bar magnets. So bar magnets have north poles and south poles, right? And so if you put the north pole of one and the south pole of the other together, they're attracted and they'll stick together. So this is like magnets, but with electrical charges. Any questions? Yes? Right. The difference is that these dipoles are always there, whereas with the dispersion forces, they come and go. It's the same concept, yes. Yep, it's the same type of attraction. The difference is that these dipoles are always there.
Because there's an electronegative?
Yeah, because of the structure of the molecule, the electronegativity of the various atoms, there is a permanent inequality of electron distribution. So the attraction is always there instead of coming and going. So polar molecules have dipole-dipole forces in addition to dispersion forces. A lot of times worksheets and stuff will ask you to identify the strongest intermolecular force that something has. And so then we kind of seem to forget that, yes, formaldehyde here has dipole-dipole forces. That's the strongest force it has, but it also has dispersion forces. So we see that polar molecules are going to have higher melting and boiling points than nonpolar molecules of a similar size. Here's formaldehyde and ethane. Their molar masses are very similar. So the strength of the dispersion force should be similar, so we don't have to worry about that messing up our comparison. If we look at their structures, we see that this one is nice and symmetrical, and it has carbon-hydrogen and carbon-carbon bonds. And remember, I asked you to remember that a carbon-hydrogen bond is nonpolar. So here we've got all nonpolar bonds. This is a nonpolar molecule. There's no permanent dipole here. In this molecule, here's carbon with 3 things bonded to it. There's no lone pairs on the carbon, but oxygen is different than hydrogen. This is a polar molecule. It's not symmetrical. So the oxygen end is going to be negative, and this carbon-hydrogen end is going to be positive. There's always this partial positive-negative charge. So we see the difference reflected in the boiling points and the melting points. Formaldehyde boils at minus 19 degrees Celsius, whereas ethane boils at minus 88. Much lower. Yes?
So if something didn't have a boiling point, then there wouldn't be a dispersion force. There was just no possible way to, or that's what they're related, right?
Yeah, so what you're thinking about is, well, what if there wasn't any force of attraction, right?
Well, I'm just trying to, why is there a dispersion force too with the addition of dipole-dipole?
Well, the dispersion force, in addition to the unequal distribution of electrons, you could have further unequal distribution that's temporary.
Oh, okay. So it'll take all.
So it's always lopsided, but sometimes it could get more lopsided, and then not, right? Okay. And we saw the boiling point of helium was 4.2 Kelvin, right? Helium is very small. It only has dispersion forces. So to get helium to be a liquid, you have to get down to 4 degrees Kelvin, 4 kelvins, because there's almost no force of attraction between them. I'm not even sure if you can make solid helium, because you'd have to get it colder. You have a question?
Also, a molecule has a higher boiling point, it's bigger, and you're saying it also has a higher boiling point.
Yes. So we have 2 factors here. There's the size. The size of the molecule affects the strength of the dispersion force. But then there's also a second force, the dipole-dipole force, that's present if the molecule is polar. So what we're doing here is we're comparing two compounds that have the same molar mass. So we can say that the strength of their dispersion force is pretty much the same. This difference is not due to one being larger than the other. It's due to this one being polar and having a permanent dipole where there's always attraction between neighboring molecules. And so you have to get to a higher temperature. These have to get a lot more agitated before they can break loose from their neighbors. These will break loose at a very low temperature because there's just not much Velcro on these guys. It's very low intermolecular attraction.
Isn't the bottom one a higher temperature?
These are negatives. So, yeah, it's a little confusing. So if we've got our thermometer here, and here's 0, one's here, and one's here. And so this one is lower than that one. Yeah. Would have been nice if they'd chosen one that wasn't just all negative numbers, but... Anybody else have any questions? Here's a comparison of boiling point with dipole moment. And so we talked about dipole moment is the magnitude of the dipole in a polar molecule. It's measured in dBs, and we said it was, and then we just said we're not going to worry about it too much. But it can be measured, right? So here we have compounds of similar size, so their molar masses are pretty similar. We would not expect much of a difference in boiling point based on that. But we do see a difference in dipole moment. As the dipole moment gets larger, the boiling point gets larger. Because this is like a neodymium magnet, one of those super strong magnets, and this is like a little weak magnet that you got in some cheapy toy, right? It's not as strong of a magnet, it doesn't stick as well. Any questions about that? The polarity of molecules is important in determining miscibility. So that's a fun word. Mixability, although it is not a word, you probably know what I mean by that, right? Mixability, the ability to mix, right? That's what miscibility means. It means it's able to mix together. We often abbreviate that or summarize that as like dissolves like. And this allows us to predict, are these two liquids going to mix together or not? And we do that by looking at, are they polar or nonpolar? Two polar substances will probably mix. Two nonpolar substances will probably mix with each other. But a polar and a nonpolar will not mix. So if they are alike in their intermolecular forces, they will probably mix. Here we have an example of nonpolar pentane and polar water. And you mix these together and they will not mix. You can shake them up, but then just like oil and water, they're going to separate out. Because the water molecules have dipole-dipole forces and they are attracted to each other more strongly than the pentane molecules that only have dispersion forces. And so these literally get pushed out of the water. So which of these molecules have dipole-dipole forces? Strange sounds from the rest of the building. Yeah, somebody broke something and seems to be upset about it. Anyway, so what are we looking for to answer this question? What kind of molecules have dipole-dipole force? Polar. So what we need to do is we need to identify which of these molecules are polar. How do we do that? might help to draw a Lewis structure, right? So carbon tetraiodide, I didn't want you to think that was Cl4, which is not a thing. This is carbon with 4 iodines. And ideally, we would count up all the valence electrons and distribute everything. But I think that most of us recognize now that carbon's going to make 4 bonds, right? Period 2, it cannot expand its octet. There's the glass going into the waste container. And so if it's got 4 things bonded to it, it's going to have 4 electron groups, and there aren't going to be any lone pairs. So this is where my shortcut for determining polarity helps out a lot. We look at the central atom. Are there lone pairs? Nope, no lone pairs, only bonding pairs. Are all of these atoms the same? Yes, they are. So both conditions are true. This molecule is nonpolar. So we can do that without thinking about shapes and vectors. Most students prefer that. Does this molecule have dipole-dipole forces? Is it polar? No, it's nonpolar, so it does not. Okay. CH3Cl. We have 3 hydrogens and a chlorine. Are there any lone pairs on the central atom? Nope. Carbon never has any lone pairs. Are all of the atoms bonded to it the same? No. The chlorine's different. The chlorine's more electronegative. And so this molecule is going to be polar. And for this question, we don't have to know which direction the dipole moment is or anything. We just need to say, is this lopsided? Yes, it's lopsided. This is polar. Does it have dipole-dipole forces? Yes. All polar molecules have dipole-dipole forces. Yes?
Can you also use like the electron or molecular geometry to tell?
Yeah. So the electron geometry for this would be the same as its molecular geometry. It'd be tetrahedral. But what's different is that one of those is not the same as the others. And so although these bonds are distributed evenly in space, they're opposing each other, one of the dipoles is larger than the others. And so they don't add up to 0. What about HCl? So if we draw its Lewis structure, we get that, and then you could ask yourself, well, are there lone pairs on the central atom? Wait, there's no central atom. Oh no, what do I do? There's only one bond.
Right, it's chlorine.
If the bond is polar, the molecule's polar. Is the molecule polar? How do we know? Are these 2 elements the same? Nope. Most likely it's polar. And in any question I ask you on an exam, that will work, okay? I'm not saying that's always true, but that's what I want you to remember because it's easy and it works most of the time. So this is polar because hydrogen and chlorine are different. So this also has dipole-dipole forces. Any questions? You see how this builds on the previous couple of chapters.
Did you say carbon-hydrogen bonds are non-polar?
Carbon-hydrogen bonds are nonpolar.
So why is B an exception?
This one is an exception because this is chlorine. If this was hydrogen, it would be nonpolar.
So they're all hydrogen.
If they're all hydrogen, or if they were all chlorine, what's important here is because there are no lone pairs, I know that the bonds, those vectors, are going to be opposing each other, spread out. If the magnitudes are the same, it'll add up to 0. But if one of them is different, then it won't add up to 0. Yeah. Good question. Anybody else? And these concepts of polarity are important in organic chemistry because it affects the properties of those compounds.
What would happen if they had lone pairs?
What would happen if they had lone pairs? That's a good question. So let's do another simple small molecule. Let's do ammonia. Ammonia has a lone pair on the nitrogen. And so because of this lone pair, these polar bonds, well, we've got 4 groups here, right? And 4 electron groups would make a tetrahedron, and so those are spread out, opposing each other. Yeah, 109.5 for a perfect tetrahedron. But then if we're looking at the magnitudes of those, the vectors for these polar bonds, here's a vector, here's a vector, here's a vector. This isn't a vector because it's a lone pair. And so I have 3 things, and they're not equally opposed to each other. Does that make sense? So the lone pair on the central atom causes it to be asymmetrical. You can draw a vector towards the lone pair, but it's not a polar bond, right? And so it can't. You could think of it a couple of ways. We're adding up the vectors, the dipole moments from bonds, and that's not a bond, so it doesn't count. Or you could say, well, I want to think of it like a bond. Well, that electron pair is different than a hydrogen. So I've got you in the second rule too. That not everything bonded to the central atom is the same, because the lone pair is different than the hydrogens. So you could remember it either way. Does that help? Any other questions? What about water? Good question. Well, if we look at water, if we don't put our lone pairs in there, we could look at that and say, well, water's linear. It's nonpolar. But water does have 2 lone pairs on the oxygens. Right? Those 2 lone pairs cause the molecular geometry of water to be bent. And so then we've got these vectors that do not exactly oppose each other because they're bent. So water's polar. Any questions? Other questions? Here we've got an electrostatic potential map for acetonitrile, CH3CN, which is polar, and they're saying this is what it looks like. So this is the nitrogen, and that's a carbon with 3 hydrogens on it. So here we've got the partial negative end, and there's the partial positive end, or we could represent it with the arrow. Both ways work. So it says, from this map, so looking at this, determine the geometry for how 2 acetonitrile molecules would interact with each other. Which of the orientations shown to the right is most likely? So here we have different combinations of 2 acetonitrile molecules approaching each other. And so this is a lot like looking at those bar magnets. And so if we had south and north and south and north, if we're looking at magnets, which of these would cause them to be attracted to each other? The top one, where the opposite poles are close to each other. This is going to cause the magnets to push away from each other. And then what if they're kind of at right angles to each other? Is that going to give a good attraction? No. So what we're doing over here is we're looking at these like they're bar magnets and saying, how are they lining up? So one way you can do this is to draw the arrow. So here, the arrow on the more electronegative end, and so this will be over here. Are those lined up nicely to be attracted to each other? Yeah, they are. So we think that's probably correct, but let's check out the others. So here and here, this is putting the two negative ends close to each other. That's like doing this. That's not going to work out very well, right? Down here, we've got this one, and this one's pointing down. So that's a little bit like this arrangement of the magnets, right? Not the best orientation for them to be attracted to each other. Does this make sense? See what I'm doing? For this one, is that going to work out very well? No. This is actually probably the worst, right? B and D are probably tied for the worst.
I have a question about the molecules where CH2Cl2.
Mm-hmm.
Because, there's two opposite C's and two opposite Cl's, does
Mhm.
that make it non-polar or polar?
I'll answer that one in a minute.
Okay.
Anybody have any questions about this problem? Okay. So the question was, what about CH2Cl2? Okay, so we can draw the Lewis structure for that. And it's got lone pairs on the chlorines, but we don't even really care about those. No lone pairs in the central atom. I can draw it like this, and it looks very symmetrical, doesn't it? What do the rules say? The rules say, I ask myself, are there any lone pairs? No, there's no lone pairs. Okay, that's good. Are all of these the same? No, they're not the same. So the rules say this is polar. And we might say, well, why? Because of three-dimensional geometry. So we got a carbon, and we've got two hydrogens, and we've got two chlorines. And these bonds are spread out three-dimensionally. They're all opposing each other. But the magnitude of these dipoles is different than the magnitude of those dipoles. And so they're not going to cancel out. That make sense? Yeah. Now, if this was something like sulfur or xenon or something where you have the potential for having extra lone pairs in there, you can have square planar molecules that could be nonpolar. But there would be lone pairs on the central atom, and so my rules still work. Any other questions? Third one, hydrogen bonding. The name hydrogen bonding sometimes misleads us because we think, oh, this is a covalent bond with hydrogen. And it does involve hydrogen that's covalently bonded, but the hydrogen bond is not the bond between hydrogen and another atom on that molecule. Hydrogen bonding is super dipole-dipole force. Dipole-dipole force on steroids, just so bulked up and strong. Right? It's just extra strong dipole-dipole force. Well, why would it be extra strong? Well, it's going to be extra strong if one of the atoms on there is very electronegative. So if we have fluorine, oxygen, or nitrogen that's bonded to hydrogen. So here we have, I believe this is HF. There's the hydrogen, here's the fluorine. This dipole moment here is extra large because the difference in electronegativity is larger than for other atoms, right? Because fluorine is the most electronegative. So this is fluorine, and that's hydrogen. So this dipole moment is very strong. And the fluorine atom is small, which means that a neighboring molecule can get close to it. If fluorine was big and bulky, then the neighboring molecule couldn't get as close, and distance is also a factor. So we have larger charges and small distance. We have a big force of attraction here. We've got partial charges are larger, and the small atoms can approach each other. So we will find hydrogen bonding in polar molecules where we have fluorine, oxygen, or nitrogen that's bonded to hydrogen. So you need to remember that. Do you remember the movie E.T.? What did E.T. want to do? Phone home, right? Phone home. You like that? I was pretty proud of that one. Fluorine, oxygen, or nitrogen bonded to hydrogen. If you see that in a molecule, you're going to have hydrogen bonding. Okay? Here we have water molecules. They have this bent structure because of the lone pairs on the oxygen. But we've got a polar molecule and we have a hydrogen-oxygen bond. So this bond is extrapolar. The charges are larger. Here's another one. So the hydrogen on one molecule is attracted to the oxygen on the neighboring molecule. This is the hydrogen bond. This is a bond between hydrogen and oxygen. That is not the hydrogen bond, the intermolecular force. Hydrogen bonding is a dipole-dipole force of attraction between two molecules. It's present when you have fluorine, oxygen, or nitrogen bonded to hydrogen. Here's another example. Here we have oxygen bonded to hydrogen. This is a polar molecule. And so we get an attraction between the oxygen on one molecule and the hydrogen on a neighboring molecule. Yes?
If hydrogen bonds are hydrogen bonding to oxygen, why aren't all of them hydrogen bonds?
So the hydrogen bond is the attraction between individual molecules. It's not the covalent bond of hydrogen with oxygen. No.
They're all like, if you look at them individually, it's a hydrogen bond with oxygen.
So this is a hydrogen-oxygen covalent bond, and this is a hydrogen-oxygen covalent bond, but those are covalent bonds. And so those are not intermolecular forces. The intermolecular force is between one molecule and a neighboring molecule. So we were just talking about dipole-dipole forces, right? Here we have two polar molecules, a negative end, a positive end. There's going to be attraction between them, right? So this is a dipole-dipole force. It's just so big it has a special name. Super dipole-dipole force. That's what I would call them, but they call them hydrogen bonds. Okay? So the hydrogen bond is this part in between the molecules. Does that help? Yeah. So it's a dipole-dipole force that's just extra strong. It's extra strong because the electronegativity difference between these two atoms is unusually large. Okay. So hydrogen bonds are between molecules. Chemical bonds, covalent bonds, are between atoms within a molecule. They are different. Okay. A hydrogen bond is only 2 to 5% as strong as a covalent bond. So even though it's super dipole-dipole force, it's still very, very weak compared to a covalent bond. Mm-hmm.
Is it wrong to say that, the dotted line, now you're saying that dipole moment, is it wrong to say that that's a polar moment? But polar moments only happen in molecules.
Well, we only have dipole moments in a molecule. And we could draw the dipole moment for water. And so here we have the positive end of water and the negative end of water, and that's the attraction between them. This is a dipole force is the force of attraction between one dipole and another dipole. So a dipole to dipole. So here's a dipole and here's a dipole, attractive force between them.
Is it wrong to say polar?
Is it wrong to say what?
To say that that's also a polar bond?
Well, they are polar bonds.
Okay, so
Yeah, so this molecule has polar bonds in it.
okay.
If all of your bonds are nonpolar, you can't have a polar molecule. But you can have a nonpolar molecule with polar bonds. Yeah. Any other questions? So in this table, we're comparing ethanol and dimethyl ether. They have the same molar mass because they have the same chemical formula, but their chemical structures are different. The way the atoms are connected is different. So that's ethanol. And this is dimethyl ether. And we could put the lone pairs in there. Is this molecule polar? Well, it's kind of hard to look at. There's too many atoms. Well, you could say, well, this atom is most in the middle. Let's call that the central atom. There's no lone pairs on it, but are all the atoms bonded to it the same? No, the oxygen's different. Hydrogen and carbon could count as the same because their electronegativities are so close, but we've got this oxygen on this side. This is a polar molecule. If we look at this one and say, well, here, the oxygen's in the middle. Are there lone pairs on the oxygen? Yeah, it's polar. These are both polar. So they have dispersion forces and dipole forces. One of them has hydrogen bonding and the other does not. Remember, we're looking for phone home. F-O-N, directly bonded to hydrogen. So here we have oxygen covalently bonded to hydrogen. That meets the criteria for hydrogen bonding. Here's an oxygen. There's hydrogens present in the molecule, but is the oxygen directly bonded to a hydrogen? No. So this molecule does not have hydrogen bonding because you have to have this oxygen-hydrogen bond or a fluorine-hydrogen bond or a nitrogen-hydrogen bond. And so we see here that the boiling points are significantly different. Ethanol has hydrogen bonding in addition to the dipole forces. And so it boils at positive 78 degrees Celsius. And dimethyl ether boils at minus 22 degrees Celsius. Yes?
So the way we can determine if it has a hydrogen bond is based off of its molecular structure?
Yeah, you have to look at the molecular structure because you have to identify, do I have fluorine, oxygen, or nitrogen directly bonded to hydrogen? So if there's no hydrogen in the molecule, there's no hydrogen bonding. If there's no fluorine, oxygen, or nitrogen, there's no hydrogen bonding. If you have two of these elements, there's a possibility, but then you have to find that bond. So here I have oxygen bonded to hydrogen. That's not the hydrogen bond, but that's necessary for a hydrogen bond. Hydrogen bonding is the attraction between this oxygen and the hydrogen on a neighboring molecule. Yes? one water molecule can't have hydrogen bonding because there's nothing for it to bond with, but two water molecules do.
How about these one for this one?
Pardon me?
How come for this one it's kind of like, and there's not two.
Well, these are both polar, and they do have dipole-dipole forces, but the dipole-dipole force on this one is super because of this bond. Oxygen pulls electron density away from the hydrogen, and it does so more than it can do with the carbon. It's kind of hard to explain. Keep asking questions.
Oh, so why is that a hydrogen? I thought it was that would just be a covalent bond within.
This is a covalent bond, but this molecule has hydrogen bonding.
Oh, is it an OH bond? Or?
So to show that, let's see, what can I do here?
I thought it was just between molecules.
It is between molecules.
Right.
So to illustrate the hydrogen bonding, I have to draw another molecule.
Oh, okay. I got you. So if there was another molecule, we would have that hydrogen bonding possible.
Yeah, that's a hydrogen.
Okay.
Yeah, so the hydrogen bonding is the attraction here.
Okay.
Yeah.
Right, because molecules don't just exist by themselves. No?
Yeah, I mean,
Okay.
in what situation would you have one ethanol molecule?
Exactly.
Now, could you arrange that? Yeah, you could arrange that, but it's not common, right? If you've got one water molecule, you've got a gazillion, literally, other molecules, right? And so they're around each other, and they will be attracted to each other. So when we look at this molecule, when we just look at the one molecule, we don't see how it interacts with the other molecules. What we're looking at is this molecule polar? If it's polar, it has dipole-dipole forces. And then we're looking for, well, does it have hydrogen bonding? ET phone home, right? One of these bonded to hydrogen. Here I've got oxygen bonded to hydrogen. That tells me that there's hydrogen bonding between this molecule and neighboring molecules. But there can't be hydrogen bonding, the intermolecular force, within the same molecule. Anybody else have any questions? Because hydrogen bonding is a very important concept, and it can be hard to get your mind around. You still have questions? Okay. Well, if you think of a question, please ask. Because I know I didn't quite answer your question. Water has an extremely high boiling point, and that's not something that we would naturally be aware of because we are so accustomed to water, right? We drink water, we bathe in water, we wash our cars, just water's everywhere. So this table is showing boiling point as a function of molar mass. And so we're looking at group 4 elements bonded to hydrogen and group 6 elements bonded to hydrogen. So CH4, Si4, germanium, and tin. And there's a trend here that as we go down group 4, the boiling point gets higher. These are going to be nonpolar molecules, and so they only have dispersion forces, but the boiling point increases because dispersion forces get stronger with larger molecules. So this is a larger molecule, the dispersion forces are stronger, its boiling point is higher than for CH4. If we look at group 6A, these are polar molecules now, and that's why these guys are higher in boiling point than their neighbors. And we also see a trend here, except for water, right? So it looks like this trend should go something like that, right? And we would expect water to be down here somewhere. But no, it's way up there. because of hydrogen bonding. None of these other molecules have hydrogen bonding. You need fluorine, oxygen, or nitrogen bonded to a hydrogen atom. Well, none of these have fluorine, oxygen, or nitrogen. Only water does. So water has super dipole force, right? Hydrogen bonding. So its particles stick together like glue. This isn't just Velcro, this is more like super glue or something. I mean, they just are really stuck together. And so you have to get to a very high temperature before they have enough kinetic thermal energy to break away from each other. Does that make sense? Which of these two has a higher boiling point, HF or HCl? HF. Good, fast answer. Why? Hydrogen bonding, yay! So if we look at these two, everything has dispersion forces, right? And these are both polar, right? Two different nonmetals. But this one has hydrogen bonding because phone home, we've got fluorine bonded to hydrogen. So one HF molecule is going to be attracted to a neighboring HF molecule. This is the hydrogen bond. It's super dipole force because this is an extrapolar covalent bond. So higher boiling point, HF. Why? It has hydrogen bonding. Stronger intermolecular forces. Any questions? There's a fourth one, which I argue is not an intermolecular force. It's a molecular ion force, right? It's not between molecules, but they put it in here, so we'll deal with it. It's called the ion dipole force. This is the attraction between an ion and a dipole. So a polar molecule attracted to an ion. And it's an important force. It occurs when you have an ionic compound mixed with a polar compound. So you can't have this force in a pure compound, only in a mixture. It's very important in aqueous solutions of ionic compounds. Well, aqueous solutions of ionic compounds are very, very common. So here we have an illustration of it happening with sodium chloride. The chloride ion has a negative charge. There's an attraction between this negative ion and the dipoles on water. So this is the ion, this is the dipole, there's an attraction between them. So all of the little water molecules, their positive ends are attracted to this negative ion. Over here we have a positive ion, and the negative ends of these water molecules are attracted to the positive ion. So all the water molecules just turn around and they're attracted. So that's the ion dipole force. That's stronger, typically, even than hydrogen bonding, because you actually have a full negative charge here. It's not a partial charge, it's a full negative charge. And this is why ionic substances can dissolve in water, it's because of this force. So this table from your textbook sort of summarizes all of this, gives us some diagrams. It's important to understand the relative strength of these. So dispersion forces are typically weakest, then dipole, hydrogen bonding, and ion dipole forces are the strongest. But there is this qualifier down here. The dispersion force can become very strong, as strong and even stronger than the others for molecules of high molar mass. So when we're comparing strength of intermolecular forces, we have to be careful what compounds we're choosing to do. And the exam questions are written specifically to not mess with you here. But how can you have a nonpolar substance that is a solid at room temperature where you have something that's polar and has hydrogen bonding like water that's a liquid at room temperature? If it's a solid, its intermolecular forces must be stronger. Well, with really large molecules, like proteins have molar masses that are hundreds or even thousands of grams per mole. Those intermolecular forces are much stronger even than the hydrogen bonding for water. But other things being equal, this comparison holds. Any questions? Personally, I like hard and fast rules that are always true, and so these kinds of things bother me a little bit because there's just way too many exceptions and things to think about. It is what it is, right? Life is messy. Which of these substances has the highest boiling point? So we're looking for strongest intermolecular force. Could any of these have an ion dipole force? By themselves, pure substances? No. So take that one off the table because you'd have to have a mixture of things. And this isn't mixtures, this is just pure compounds. So we have CH3OH, we have CO, and we have N2. So we're looking for the strongest intermolecular force. So do any of these have hydrogen bonding? Yeah. Which one? A. The way these formulas are written suggests how the atoms are connected, right? So CH3, the H3, those are connected to the carbons, and then we've got hydrogen and oxygen. And so this is representing a Lewis structure like this. And if you try to draw that Lewis structure, you're not going to be able to draw it without having an oxygen-hydrogen bond. So this one's got hydrogen bonding. So we would predict that that's going to have the highest. We should think about size. Are these kind of close in size, or are they hugely different in size, in mass? They're different, but are they crazy different? This one has a molar mass of 28, and this one is also 28, 16 and 12, right? And then this one is, 32? So those are close. If one of these was 150, then we'd have to worry about, that one's got stronger dispersion forces. But these are similar in size. So the highest boiling point is the one with the strongest intermolecular force. Which would have the lowest boiling point? Nitrogen. Because this one's nonpolar. This only has dispersion forces. This is a polar molecule, so it has dipole-dipole forces. So this would have a lower boiling point than carbon monoxide. So hydrogen bonding is very important in many physiological processes. And here's an illustration of how it works in your DNA. So each strand of your DNA is composed of a chain, a backbone of phosphate sugar molecules stretched together in a chain. And that's what's represented here with the ribbon. And onto the sugars is attached a base. These are the different bases: thymine, adenine, cytosine, and guanine. And so here we show the bases hanging off the backbone. Those are these bases up here. So thymine and adenine can do hydrogen bonding because we have an oxygen here, and that can that's going to be electronegative and will be attracted to this hydrogen. We have this nitrogen-hydrogen bond, and here's a nitrogen-hydrogen bond. And so these two can match up and form two hydrogen bonds. Cytosine and guanine, when they match up, they can form three hydrogen bonds. And so it's kind of like little interlocking toys that these two match up together and these two match up together. So in the DNA, what's holding the two strands together is the hydrogen bonding between the base pairs. So adenine to thymine, we have two hydrogen bonds. Cytosine to guanine, three hydrogen bonds. The exact order of those base pairs is what causes people's hair to be different colors and eyes to be different colors and all kinds of other interesting things. DNA molecules are very, very long, right? Thousands and thousands of base pairs. Your body can make new DNA by separating the old strand. The two strands are not identical to each other. They're complementary. Where one has guanine, the other has cytosine. So they're not exactly opposite, but they're complementary to each other. But we can pull those two strands apart and form a new strand that's complementary to the first strand. And what happens is you get ribosomes, and they come along and they bring in the base pairs that match up, and then it comes behind and fills in the chain, hooks up the chain. It's really kind of cool. And then you can make another strand over here, and what you end up with is two strands that are identical to the first strand. Hydrogen bonding. Any questions?